Here we go. Okay. So I do kind of want to, I'm not going to go through all of chapter 12 again, of course, but I just want to recap why these z-scores are so useful. Okay. I mean, again, suppose we have a normal distribution. In other words, you have data values that can be described by a normal distribution. Okay. Such as a normal distribution curve. It may not be exact. It may not fit the curve exactly, maybe only approximately. But, in the real world, that may be good enough. Not everything fits theory 100%. But anyway, suppose we do have a normal distribution curve. Suppose we have two numbers, A and B, okay, such that A is less than B, okay? And let's say, we want the percentage of data values somewhere relative to A and B. So for instance, let's say we wanted the percentage of data values from the normal distribution less than A, okay? Less than A. Well, it turns out that percentage can be found by the area under the curve of the normal distribution curve to the left of A in this case, to the less than A, to the left of A. You're finding the corresponding area under the graph of the normal distribution curve. That's really what you're looking for. It's kind of like that empirical rule. If you want, approximately about 68% of the data, for instance, lies between two certain values, we're kind of generalizing that a bit, in a sense. But how do we get this area? I mean, this shape is not something simple like a rectangle or a triangle or a circle. It's not obvious how we can get that shape. I mean, it's not obvious that if you get the total area under the entire graph, it may not be obvious that it's going to equal 1. That takes a lot of calculus, but we're not going to do that. I guess for now you'll have to take my word for it. But to actually get that area, what people do is they convert this A, in this case, the data value, to the z-score. We've done that before. And then they get the corresponding area under the standard normal distribution curve. So they convert the data value to the z-score, well, standard score, same thing. They get the area under the standard normal distribution curve. I mean, that's a little bit easier to deal with because the mean is 0 and the standard deviation is 1. And people have analyzed the area under the graph of the standard normal distribution curve. People have analyzed that. And that you can actually find using a table of values in the book. We'll get to that shortly. But that's really what people do. So you're getting percentage of data values less than this standard z-score. And if you wanted the percentage of data values between A and B, A and B are two data values, you would find the z-scores for A and B and get the area between the z-scores. And if you wanted the percentage of data values bigger than A, you would have to get the area bigger than the z-score. The area to the right of it. The area to the right of A, the percentage of data values greater than A. You want the area to the right of A. You get the z-score, and you look at the area to the right of the z-score under the standard normal distribution curve. So essentially, you're getting the corresponding area under the standard normal distribution curve. Instead of the data values, you're using the z-scores. That's really what it boils down to. I mean, that's what these graphs are trying to illustrate. And again, this is what I'm also trying to say here. For the area under the original normal curve to the right of A, that's equal to the area under the standard normal distribution curve to the right of Z sub A. So again, if you wanted the percentage of data values bigger than A, you want this area, in other words, to the right of A, under the graph, under the curve, excuse me, and that area is equal to the area to the right of the standard z-score under the standard normal distribution curve. Okay. And also, if you wanted the area between the x equals a and x equals b under the original normal curve, meaning you want the percentage of data values between a and b, again, you want the area between a and b under the normal curve. It's the same as the area under the standard normal curve between these two z-scores. Okay, that's what it boils down to. So essentially, you're getting the corresponding area. To get the percentage of data values, you want the area under the normal curve. And what you do is you get the area under the standard normal curve between the standard z-scores. I mean, I hope this is making sense. The whole idea is you're converting the data values to the standard z-scores. You're getting the corresponding area under the standard normal distribution curve. Now, this isn't easy to calculate, but we don't have to do it directly. We have Desmos, as you'll see. We also have the textbook. Okay? Actually, let me show you guys now. Let me show everyone now the textbook the page in the textbook I'm referring to. There it is. Let me just stop sharing this for a bit. Yeah, I really hope it's making sense what I'm saying, but I think it is. But this is the page I'm talking about in the book. This is the area to the left of that z-score under the standard normal distribution curve. So to the left of -3, the area is this. And also, since you're getting percentage, you want to convert the area to a percent. So we will use this table from the textbook. You could actually get the area using a calculator. The book does go into that. So I'll let you read that on your own. Excuse me. So that's what the table is. So if you wanted the area to the left of the z-score, 0.8, right? You would find the z-score, and then to the right, you would get the area. So for 0.8, the area would be 0.7881. And that's the same as saying 78.81% of the data values are less than the z-score 0.8. All right. So that's good. So hopefully that made sense. Let me now go back to the notes and let's move on. I'll also show you how to get that stuff using Desmos. I mean, with Desmos, maybe the z-scores are not as important, but it's still good to be able to use the z-scores. All right, cool. Are there any questions about that, what I'm trying to say? Yeah, I really hope it made sense. All right. Okay. So this is from an earlier, wait, what am I? Can I have one? Okay, let me here. So this is actually from an earlier example. Suppose we have test scores. I gave a test in class or something. The test is at a 30. It turns out the test scores are normally distributed with a mean of 17. The standard deviation, let's say, is 2.5. And let's say we want to know what percentage of students scored less than 15. In other words, what percentage of the test scores are less than 15? Well, we have a normal distribution, right? Let's get the z-score. So for 15, remember, how do you get the z-score? It's the data value minus the mean divided by the standard deviation. So again, it's the data value minus the mean divided by the standard deviation. So for 15, we're going to have minus 2 over 2.5. I put the minus in front, but algebraically you can do that. And this turns out to be negative 0.8. So again, we want the area under the graph of the normal distribution to the left of 15, and that's the same as the area under the standard normal distribution to the left of negative 0.8. We want the area to the left of negative 0.8. Okay, well, it's from the table. I wrote the answer here, but let me go to the table and show you. Stop sharing this again. All right, here it goes. Here we go. So if you look at negative 0.8, you may have to, let me see if I can zoom in. Although, I don't know if that'll affect anyone else. But if you look at negative 0.8, okay, hopefully you can see it's in the second z-score column from the left, and you go down to negative 0.8. The area is 0.2119. So the area to the left of negative 0.8, that z-score, is 0.2119. That's the area we're looking for. And that means the area to the left of 15 under the normal distribution curve, with this mean 17 and standard deviation 2.5, is 0.2119. Area, we convert it to a percent though, so about 21.19% of the data values are less than 15. So about 21.19% of the test scores are less than 15. That's really what I'm trying to say here. And let's do the same thing for 22. For 22, okay, it's really the same idea. You get the z-score, so you have the data value, minus the mean, divided by the standard deviation, which is 2.5. Okay? Then that's going to be 5 over 2.5, which is 2. And if you went back to the table, so I guess I got to switch it up again. For 2, let's see, it's in the z-score column, the first one from the right, down 1, 2, 3, 4, 5, down 6 rows from the top. You get 2.0, and that area is 0.9773. So the area to the left of 2 under the standard normal distribution curve is 0.9773. So that means, because of that, the area to the left of 22 under the normal distribution that we're dealing with is 0.9773. In other words, 97.73%. Wait, let me get back to the notes. Yeah. So in other words, about 97. So the area to the left is 0.9773. So about 97.73% of the data values are less than 22 under the normal distribution curve given the test scores. So in other words, the answer is about 97.73% of the test scores are less than 22. This should not be, got to change that. There we go.